Hi, this is just a short video on the Fulkerson algorithm for max flow. Just a bit of introduction. What is the problem that this algorithm attempts to solve? The Fulkerson method is an algorithm which computes the maximum flow in a flow network. The flow network needs to have a single source and a single sink. This algorithm was first published in 1956 by L.R. Ford Jr. and D.R. Fulkerson. The big picture. Just to give you a basic idea, as long as there's a path from the source S to the sink T, with available capacity on all edges in the path, we send flow along one of these paths, then we find another path and so on. When there is no such path left from source S to sink T, the algorithm ends with the maximum flow network. Before we carry on, I just wanted to introduce the terms that are being used here. Flow network. A flow network is a directed graph where each edge has a non-negative capacity and receives the flow. The amount of flow on an edge cannot exceed the capacity of the edge. Max flow. This involves finding a feasible flow through a single source, single sink flow network that is maximum. Augmenting path. A path in the residual network GF with available capacity is called an augmenting path. That is a simple path from source S to sink T that can admit more flow. What is flow? A flow f in the network G is a real-valued function that satisfies three properties, the first being capacity constraint. It simply states that the flow on an edge cannot exceed its capacity and cannot be negative. The second being flow conservation. Except the source and the sink nodes, the net flow at every other node has to be equal to zero. That is, the amount of flow going into a node has to be equal to the amount of flow coming out of that node. The third being skew symmetry. The basic idea behind this is that a flow from U to V can be interpreted as a negative flow from V to U. Also note that if there is no edge between two nodes, there can be no flow between these nodes. The value modulus of f of the flow function f is the total flow out of the source minus the total flow into the source. Given above is an example of a flow network. The graph on the left shows the capacity of each edge, whereas the graph on the right shows the flow. This also happens to be the max flow graph in this case. For example, the edge from B to D has a capacity of 40 and a flow of 10, which is written as 10 over 40, hence holding the capacity constraint property. It also holds the flow conservation property. For example, the flow into A from S is 80 and from C is 10, a total of 90, whereas the flow out of A to B is 60 and to D is 30, a total of 90 again, hence making the net flow at node A 0. Also note that flow networks are meant to be graphs, and for convenience, edges with zero weight haven't been shown. Problems with max flow networks. If there are multiple sources or sinks, we add a new source or a sink node and join the previous sources or sink nodes to this node. These new edges can ideally have a capacity of infinite amount. Also, if there are anti-parallel edges, we remove one of the edges by creating a new node and joining the edges to this node accordingly. Here's an example to show the max flow problems. The graph on the left has multiple sources S1 and S2. So to a single source, we add a new source S prime and add edges with infinite capacity from this node to all the previous source nodes, here it being S1 and S2. The case where there are multiple sinks is taken care of in a similar way. Had there been an edge from A to C, we would have had to create a new node, say X, and create an edge from A to X and another edge from X to C to take care of the anti-parallel edge problem. Fourth Fulkerson method. Given a flow network G equals to VE and a flow F, the residual network of G induced by F is GF equals to VEF, where EF has three different cases. The first being, it'll be a forward edge from U to V with the flow of its capacity minus its previous flow in the flow network. The second being, it'll be a backward edge from V to U with the flow as its flow from U to V in the flow network. The third being 0. The residual capacity of an augmenting path is the value of the edge with the minimum capacity on that path. This is also vague to you right now, but I am sure it will be a lot clearer with an example. Here's an example of a residual network. The graph on the left is the flow network G, and the graph on the right is its corresponding residual network GF. Let's take an example. If we take the example of an edge from A to B on the flow network, it's got a capacity of 60 with a flow of 50. So in the residual network, we still have the same edge, but the values change now. the new value that edge gets is it's its capacity minus the previous flow, so that's 60 minus 50. That gets you a value of 10. Basically, this just means that that edge still is there to show how much more flow can be admitted through that edge. And then we have a backward edge from B to A with the value of the previous flow, that's 50. And it's the same thing with all the other nodes as well and the edges as well. Augmentation. This is just basically adding the increase in flow found in the residual network to the flow in the flow network. So if F is the flow in the flow network, and if F prime is the flow in the residual network, and for each particular edge, when we add this F and F prime, we get a new value for the flow in the flow network. For Fulkerson algorithm, the Fulkerson method is pass the graph, the source, and the sink. The first thing we do is to initialize the flow to 0. Then we run a loop to check if there is any augmentation path in its corresponding residual network G of F. If there is a path that's found, we augment the flow along P in the flow network. We carry on doing this until we reach a situation where there are no such paths left, and then the program breaks out of the loop. At the end of this, the flow network that's remaining is the maximum flow network, and the whole program ends that way. It'll be a lot clearer with an example now. Here's an example to solve the max flow problem using the Fulkerson algorithm. Picture A is just a simple flow network. Picture B is the same flow network with a flow of 0, as mentioned in the algorithm. Then picture 1A is this corresponding residual network, which happens to be the same as the flow network since the flow is 0. Now we look for a path which can get you from S to T. It can just be any random path. So in this example, I've chosen S to A to B, B to T. Now we try and find the residual capacity of this path. That's 50 because that's the minimum, the edge with the minimum capacity on this path. That's B to T is 50. So we now augment this path, and hence we get a new flow network that is got a flow of 50 from S to A and a flow of 50 from A to B again, and a fifth flow of 50 from B to T. We carry on doing for the new flow network. Shown in 1b, we find its corresponding residual network shown in 2a. For example, the edge from S to A had a capacity of 90 with a flow of 50, which now gets a new value of 90 minus 50, that's 40. This simply shows that this edge can admit more flow in that direction. But there's also a back edge from A to S, which has a value of 50, and this same concept carries on with the other edges as well. Now we choose another new path from S to T on this residual network. So here we've chosen S to C, C to D, D to T. We find the residual capacity, that's 30 in this case, and we find its corresponding flow network by augmenting the path. Then we carry on, we find the new residual network. Now we choose another path that's S to C, C to A to B, B to D, D to T. Find the residual capacity, that's 10, and augment the path and find its corresponding flow network, which is shown in 3B. 4A shows the residual network corresponding to the flow network shown in 3B. We now look for another path, so it is a path from S to A to D, D to T. Then we look for a residual capacity, which is 30 in this case. We augment this path and get the new flow network, which is shown in 4B. Now we find its corresponding residual network, which is shown in 5. We look for another path from S to T, but when we get to A or we get to C, there's no way we can get to T from there, so there is no path. That means the program comes to an end, and then the flow network found before that is the max flow network. That's with a maximum flow of 80 plus 40, that's 120. Time complexity. The running time of this algorithm depends majorly on the way the augmentation paths P are chosen. The algorithm only terminates if there are no more augmentation paths remaining in the residual network, but there is no certainty that this situation might be reached. So the best we can say is that the algorithm is bounded by big O of EF. E is the number of edges, that is, each augmenting path that can be found takes E time and increases the flow by at least 1 each time, and F is the maximum flow in the graph that denotes a bound in the number of iterations. This can be slightly improved by a modification of this algorithm, which is known as the Edmonds-Karp algorithm, which has a time complexity of big O of VE square. Thanks for watching.